Greetings, Panthers. Dr. Augustine again. Today we are going to look at an example of a calorimetry problem. This is actually the second example of calorimetry problem. The first video, my introduction to calorimetry, we did a calorimetry problem of like having a hot piece of iron, putting it in a cup full of water and we're actually measuring the specific heat, but measuring the heat flow from the hot metal into the colder water. This one we're going to do a reaction, dissolving a salt in water. So here's the equation. Calcium chloride, solid calcium chloride, dissolves into calcium ions plus 2 chloride ions. So 1 mole of calcium chloride yields 1 mole of calcium ions plus 2 moles of calcium chloride. We have a delta H for this reaction. So this, if you recall, this is called a thermochemical equation. When you have a balanced chemical equation plus you have a delta H value associated with it, we call that a thermochemical equation. And we note it's a negative sign here, which tells us when it dissolves, it's actually giving off heat. So the water around it should get warmer. If we were to put our hands on this and feel it as it was dissolving, we would notice that the water was actually getting hotter. And remember also that this minus 81.5 kilojoules is related to the stoichiometry. So it's minus 81.5 kilojoules for every 1 mole of calcium chloride. So if we dissolved a mole of calcium chloride in water, it would release 81.5 kilojoules. So here's the problem, and this is a pretty typical problem. We have an 11-gram sample of calcium chloride. The molar mass is 110.98 grams per mole. So this is not a mole. It's about 1/10 of a mole, significantly less than a mole. So we're not going to get 81 kilojoules. We're going to get about 1/10 of that. It's dissolved in 125 grams of water. Both substances are at 25 degrees C. We're looking to calculate the final temperature of the solution, assuming that no heat is lost to the surroundings and assuming the solution has a specific heat capacity of 4.18 joule per gram degree C. So that's the same heat capacity as water. So here's what we're trying to do. We are trying to find the final temperature of this reaction after it takes place. We're trying to calculate the final temperature as this reaction takes place. All right, so here's how I like to approach these problems. I like to actually sketch out what's happening. So we've got a coffee cup calorimeter. We've stolen this from the dining hall. And we have a thermometer over here. We have some water. In this case, the mass of the water is equal to 125 grams. The temperature of the water, temperature initial of the water, is equal to 25 degrees C. And we are dissolving into this some calcium chloride. So we have some calcium chloride salt. The amount we have is amount of calcium chloride is equal to 11.0 grams. And we know the molar mass. So that's the setup that we have. One more piece of information here. The specific heat of the solution after we make it is 4.18 joules per gram degree C. Okay? That's our basic setup. Now, I want to point something out that is a common mistake for students to make, and I want to show you why this is not the way this problem is set up. So because this says 11-gram sample of calcium chloride, a lot of students are going to latch on to that 11 grams. And the reason why they're going to latch on to that 11 grams is we know that there's 3 flavors of Q that we could possibly use. Q could be equal to MC delta T. Q could be equal to capital C delta T if we have the heat capacity given to us, or Q sub P at a constant pressure could be equal to delta H. So a lot of students, when they see a problem like that, like this, will naturally gravitate towards this one right here, Q equals MC delta T. The reason why they do is they see there's a mass, they see there's a temperature, it's 25 degrees C, it's 11 grams of sample, and they think, MC delta T, that has to be it. Here's the problem with that. We don't know what C is for calcium chloride. Okay, we're not sure. We can't just look up in the table what C is for calcium chloride. And besides the fact, that's solid calcium chloride. Even if we could find a C value for solid calcium chloride, we don't have solid calcium chloride. It's dissolving in solution. That's what the chemical reaction is. Okay, so we can't just look up what's the chemical reaction. It's given to us by this equation, this delta H. So actually, we need the third type of Q. We need Q equals delta H, or is related to delta H at least. So this is a very common mistake for students to make. I want you to recognize it at this point, that we are not going to use MC delta T, at least for the calcium chloride part of it. Now look, we're dissolving this in water, and we have a mass of water, we have a temperature of water, and we have a specific heat of the solution. So we can use MC delta T for the water part of the equation, but not for the calcium chloride. Okay, careful, important idea here that a lot of students make a mistake with. So let's continue with this problem, and we're going to start, like I said, to start all these problems. Q total equals to 0 equals to Q sys plus Q surroundings. And this might be a good time to stop the video and see if you can figure out what the system and what the surroundings are. You should end up with 3 different things. So if we think about Q sys plus Q surroundings, well, the system is clearly made up of this chemical reaction right here. This dissolution reaction is definitely part of the system. So the way we write that is we say Q reaction. We're actually interested in the chemical reaction that takes place. That's part of the system. And we can say the water is the surroundings and the calorimeter. That's fine. So QH2O plus Q calorimeter are all the other things that are involved. So just to recap, I always start with this equation. Q total equals 0 equals Q sys plus Q surroundings. Now we need to figure out what makes up the system and what makes up the surroundings. The system is this chemical reaction. It's us pouring 11 grams of this into the water, it dissolving, and then releasing heat. So we express that with Q reaction. The surroundings are the water that it goes into plus the calorimeter. Now, once again, assuming no heat is lost to the surroundings and assuming a solution has specific heat, that little hint right there tells us Q calorimeter is equal to 0, which is going to make this a little bit of an easier equation to deal with. So 0 equals Q reaction plus Q water. Okay, at this point, we're going to move one or the other of these over to the 0 side of this equation, and it's a good idea to think about what's happening. So because this is an exothermic reaction, because this is giving up its heat, it makes sense to put the reaction as the negative side. I think I mentioned this in the first video. You can get away with this if you don't do this. This isn't essential, but if you do this, it just makes your life a little bit easier. Okay, so there is our key guiding equation. Q reaction equals QH2O. If you can get to this point, you've made significant progress. Now we need to go and figure out these 3 flavors of Q. How am I going to plug them in? I'm trying to find Q reaction, and I'm going to relate it to this minus 81.5 kilojoules. Let me tell you how I'm going to relate it. I know it's minus 81.5 kilojoules if I have 1 mole of calcium chloride. I only have 11 grams of calcium chloride, therefore I'm going to end up with less delta H. This Q is going to be less than that. So the way we're going to measure this is we're going to measure the change in the temperature of the water. So the Q water is the thing we're actually going to use to help us figure out what this is. So negative Q reaction, and I should really note this water, this is actually the new solution that's formed. So we really should call this Q solution, not Q water. So Q reaction is equal to M solution times C solution times delta T of the solution that's formed. All right, so minus Q reaction then is going to be equal to the mass of the water is 125 grams. C solution is 4.184 or 4.18 joules per gram degree C. And delta T is equal to the starting temperature, which is 25 degrees, or final minus initial, is T final minus T initial. Okay, and if we cross some units off here, we're going to notice that grams is going to cancel grams, and this is going to be in degrees C, so degrees C is going to get canceled. This is going to give us a Q reaction number. All right, so we got a couple more things we need to plug into this before we can actually try to solve this problem. Remember, we're trying to find the final temperature. This is what we're trying to find. So this is equal to 125 grams times 4.18 joules per gram degree C times TF minus 25 degrees C. Okay, so right now we have one equation with two unknowns. We've got Q reaction that's unknown. We also have this TF that's unknown. We're trying to find TF. So we're going to need to figure out what this Q reaction is. And that's where we come back to our original equation. So let's think about how to deal with Q reaction. All right, so Q reaction is going to be related to the delta H value in the equation. It's going to scale with the delta H value. In other words, if we had a mole of stuff, I would know the Q reaction was minus 81.5 kilojoules. We don't have a mole. We only have 11 grams. So what we need to do is we need to find out how many moles we actually have, and then we need to do a simple calculation that related to a thermochemical equation. So let's do that. So let's find out how many moles of calcium chloride we have. So moles calcium chloride is equal to 11.0 grams CaCl2 times 1 mole CaCl2 for every 110.98 grams CaCl2. Grams cancels grams, and this gives me 0.0991 moles CaCl2. All right, now I can find out how much heat was evolved in this reaction, and I'm going to start with the number of moles, 0.0991 moles CaCl2 times, we're going to use this factor and this thermochemical equation. This is a one-step calculation, minus 81.5 kilojoules for every 1 mole of CaCl2. Moles is going to cancel moles, and that is going to give me 8.078 kilojoules. And I need to keep that negative sign in there. It's releasing 81.5 kilojoules per mole. So I have negative 8.078 kilojoules. So now we've almost got it. We could plug this back in. We got one small problem, and that is this one's in kilojoules, and this is in joules. And since we're trying to find, well, we could either convert this one to kilojoules or put this one in joules. It's probably easier to put this one in joules. So I'm going to say times 1,000 joules for every 1 kilojoule. Kilojoules cancels kilojoules, and that is going to equal to negative 8,078 joules. That's my Q reaction. Okay, so now I'm going to plug this back in here. So negative minus 8078 joules is equal to 522.5 joules times TF minus 25.0 degrees C. Okay, now we're just going to solve for TF, and I'll let you convince yourself of this, but 40.4 degrees C is my final temperature when you solve for TF. The units should all cancel. The degrees C here would have canceled with the degrees C. The grams would have canceled with the grams. You would have been left with joules on this side, and our final answer is going to be in degrees C. Does make sense also. We start at 25. We know this is exothermic, so the temperature should go up. So the temperature would go up to 40 degrees Fahrenheit. Okay, let's just recap the key points to this. So the key points to this are we have a coffee cup calorimeter. We are dissolving a certain amount of this solid in there, but it's the chemical reaction that's actually doing the heat. Okay, it's not the piece of iron that's giving off heat. So we are not going to use MC delta T for the reaction side of this equation. We're going to use this balanced thermochemical equation. Now, a lot of times you'll be going in the opposite direction. You're actually going to be trying to find what delta H is. So you'd be solving for Q reaction. But this time, we know the thermochemical equation. We know the number of moles we had, so we calculated the number of joules. That was our Q reaction, and then plugged it back into this equation and solved for T final. All right, thanks for watching. I got one more video to do, and that one is going to be calculating the molar enthalpy of a reaction.